Hello, welcome to Introduction to Composites. This is the start of the 6th week of this course, and what we plan to do over this period is have a detailed discussion on how to predict different values and different properties of unidirectional composites. Last week we had started this theme and we had covered specifically how to predict the density of a unidirectional composite material. And then we had just started discussing prediction of longitudinal modulus of composite, and we closed last week by having a discussion of how do fibers and matrices fail, because that discussion will constitute the basis of our initial discussion on this week, because what we plan to start from today is discussion, a detailed discussion on how do unidirectionally composites fail, especially when they are loaded in tension along the length of the fiber. So, that is what we plan to discuss today. So, what we will discuss is failure of unidirectional lamina loaded along fiber direction. So, what does that mean? What it means is that suppose I have a unidirectional composite and the fibers are aligned along the length of the composite, and suppose I apply an external load sigma L. Why do I call it sigma L? Because it is in the longitudinal direction. We had defined longitudinal transverse and transverse prime directions in the last week. So, I am applying the external load in the direction of the fibers, and because of that load the stress in the composite is sigma L. Then I want to discuss how does this lamina or this composite, which is unidirectional in nature, it fails. So, just a very quick overview. In the last class we had discussed in detail about the failure of how do fibers fail, how do matrices fail. So, we will very quickly review that and then extend that understanding to failure of this type of a composite. So, if I have a piece of matrix material, initially it is linearly elastic and then it starts becoming somewhat plastic, and slowly this slope becomes almost 0 and then it fails at a particular point. So, this strain at which the matrix is failing, I can call it epsilon mu, ultimate strain in the matrix at which it fails, and the corresponding stress at which it fails, I can call it sigma mu. It is the ultimate strength at which this matrix is failing. For fibers, we had discussed two different types of fibers. One was an elastic brittle failure and the other one was a ductile failure. So, if the fiber is brittle in nature, typically these fibers are much more stiff than the matrix. So, if the fiber is brittle, then let us say I keep on pulling it, it takes on more and more load, and at a certain stress level it just cracks and the fiber fails catastrophically. So, this is the case of a brittle fiber. and this value would be sigma Fu, which is the ultimate fiber strength. Now, if the fiber is not brittle but ductile in nature, then at a certain point it starts behaving plastically, and at some point it again fails. This is for a ductile fiber, and this curve is for a brittle fiber. This is for a brittle fiber. Now, in case of a composite, how would this kind of a composite fail? It will depend on several things, but first we will draw a graph for it and then we will develop some mathematics around it. So, if there is a composite material which has fibers all in the same direction, and if I keep on pulling it, typically what will happen? If I pull that composite, essentially what is going to happen is that the composite is going to become longer, right, and we note that typically the failure strain of fibers. So, what is the failure strain of fiber for the brittle fiber? For the brittle fiber, this is epsilon Fu. This is the failure strain. So, we see that for brittle fiber as well as for the ductile fiber, the failure strain of matrix is much more than the failure strain for the fiber. Does not matter whether it is a brittle or a ductile fiber, but typically matrix becomes very elongated and only then it actually fails. So, with that understanding, when I am pulling this material in the length direction, what will happen? The fiber starts becoming longer and the matrix also starts becoming longer, but once the strain in the fiber reaches its breaking point, the fiber will fail. The fiber will fail, and so consider this. So, let us say this is matrix and this is fiber, and I am pulling it like this, and as I pull it, the strains in the fiber and matrix, because they are going to be the same, because I am pulling it by the same amount, and as I keep on pulling it, at some point what will first fail is the fiber, because it breaks at a smaller strain point. So, once the fiber breaks, all this material is no longer taking the load. So, at the breaking point, let us say fiber takes Pf, total amount of load which is being taken by the fiber is Pf, and the load which is being taken by the matrix is Pm, and if I add these two these two things together, then P composite is equal to Pf plus Pm, right. So, initially as I keep on pulling it, there is a stress in the fiber and load in the fiber and load in the matrix material, and the sum of these loads is equal to load in the composite Pc, but at some strain level the fiber breaks, and what happens? But I am still applying the same amount of load. Suppose I have applied 200 kilograms of load on a piece of material, that 200 kilograms is still there, that is Pc. So, where does all that load go? This Pf, all of a sudden once the fiber fails, it becomes 0, all that extra load is shared by Pm. Okay. Now, it depends, if the cross sectional area of matrix is very large and the cross sectional area of fiber is very small, then the amount of Pf will be very small, right. Suppose I have only one single fiber in the composite, only one single fiber, then the amount of load which will be carried by the fiber will be extremely small, negligible, and that load will get transferred to the matrix and matrix will be able to bear it. So, then I can still apply more and more load, and then once the matrix fiber matrix breaking strain is reached, then the matrix fails. So, that is one case, and that is the case when the amount of fiber in the material is extremely small. If the amount of fiber in the material is reasonably large, and we will find what is the meaning of that reasonably large term, then what will happen? The magnitude of PF will be significantly large, and all this load gets transferred to the matrix, and all of a sudden matrix has to now bear a very high amount of load, but the breaking stress in the matrix is not very high. It is sigma mu, which is much less than sigma fu, right. So, because it cannot now all of a sudden handle such an extra load, matrix also fails immediately. So, we have two types of situations. If fiber volume is very small, volume fraction of fiber is small, I keep on pulling it, fiber breaks, whatever is the extra load that is not large enough, it gets transferred to matrix, and the amount of that extra load which is now transferred to matrix is not large. So, matrix can handle this extra load, and I keep on pulling. So, the composite does not break. So, now I have to pull the matrix even more, and then the matrix breaks. The second situation is that if the volume fraction of fibers is large, then once the fiber breaks, the amount of load which is transferred to matrix is significantly large, and at that point of time matrix cannot handle that extra load. So, matrix also breaks. So, the entire composite fails. So, these are the two failure scenarios for composite. So, now we will develop the relation for both these scenarios. So, the first one is case A. Okay. What is the in this case here? What is the situation? As load is increased, first thing is fibers break, okay, and then once the fibers break, what happens? Load of fibers gets transferred to matrix. This load, this additional load on matrix is not very large. Hence, matrix can handle extra load So, when matrix can, so now as external load is further increased, what happens? At some point composite fails. So, this is the first case, and this case happens when Vf is very small, because if Vf is large, then the load transferred will be reasonably high and matrix will not be able to handle it. So, in this case we will find what is the value of sigma Cu, which is the ultimate tensile strength of the composite, So, again we will draw a picture. So, let us say this is fiber and this is matrix, okay. and I am applying a load of P. Okay. So, what is, and let us say the cross sectional area is A. Okay. So, sigma F will be what? It will be P by A into volume fraction of fiber. So, P by A is what? Sigma C, stress in the composite, times volume fraction, and sigma M is again P by A into volume fraction of matrix is sigma C V M. Now, these are the relations before breaking, before fiber break. These are the relations before the fiber breaks. At the point, once fiber breaks, what happens? Once fiber breaks, all the load is being shared by matrix only. All load is shared by matrix. Okay. All the load is shared by the matrix. So, in that case, sigma F, the stress in fiber is what? Is 0. And the stress in matrix is what? What is the stress in matrix? Well, total load is, external load is force, and what is the area of matrix? Area times Vm, right? This is the area of the matrix. So, this is sigma C by Vm. So, once fiber breaks, all the load is shared by matrix only. So, this is the stress in the matrix. Now, as I keep on increasing my sigma C, as I keep on increasing my sigma C, sigma M also increases, and once this sigma M reaches sigma mu, this sigma mu. So, once sigma M equals sigma mu, matrix breaks. So, at this point fiber has broken and matrix has broken. So, entire composite has failed. So basically so the condition for, condition for failure is sigma mu equals sigma C by Vm, right? Sigma mu is equal to sigma, and at that point, and that is what I call sigma Cu, that is what I call sigma Cu. So, this is actually sigma Cu, ultimate strength of the composite. So, I can write sigma Cu equals Vm times sigma mu, and I know that Vm is what? 1 minus Vf. So, the strength of composite for case A. What is the strength of composite for case A? Sigma Cu equals 1 minus Vf sigma mu, and this is when Vf is very small, and we will define how small it has to be later. But and when Vf is extremely small, fibers break, and at that time all the extra load from fibers get transferred to matrix. Matrix can still absorb that extra load. So, now I can keep on loading it further, and finally the matrix will fail, and the matrix will fail when the stress in the composite sigma Cu equals 1 minus Vf times ultimate tensile strength of the matrix material, ultimate strength of the matrix material in tension. Okay. So, this is case A. So, we will now do case B. In case B, so in case A, what did we say? In case A, we said that as load is increased, initially the fibers are going to break, load of the fibers gets transferred to matrix, and this increase in the load of matrix is not sufficiently high. So, matrix can handle extra load. So, matrix takes the external load. So, I can still further increase my external load, and as I increase it beyond the threshold, the matrix also fails. In case B, that is not the situation. So, in case B, as external load is increased, 1, fibers break, extra load from fibers gets transferred to matrix. Third, this increase in matrix load is so high that matrix cannot absorb it. It cannot absorb it. So, fourth, so matrix also breaks immediately. So, we can say that fibers, matrix and composite fail at same load. This is the condition. Fibers, matrix and composite fail at the same load, or I will say at the same strain level. I will not call it load, it can create confusion. They fail at the same strain level. Okay. So, look at this. So, in this case the fibers, the matrix and the composite, they fail at the same strain level. And what is the strain level? That strain level, that is epsilon Fu. Now, this epsilon Fu could be a little higher for ductile fibers or than for brittle fibers, but it is very small. But they will fail at the same strain level, which is epsilon Fu. Fu means fiber strain, ultimate breaking strain in the fibers. At the breaking strain in the fiber, what is the stress in the matrix? That stress, if I look at this picture, is this level, right. So, at this strain level epsilon Fu, the stress in the matrix is what? This stress is sigma m at epsilon Fu level, right. So, it corresponds to this point on the green curve. So, at this stress, so at the stress level, at the strain level of epsilon Fu, what is the stress in the fiber? In the fiber the stress is sigma Fu, and in the matrix the stress is sigma m at this strain level, which is epsilon Fu. Understood? Okay. So, now let us look at this picture. So, here this is my fiber and let us say this is my matrix, and I am pulling it with a load P, I am pulling it with a load P. So, what is the stress? Stress in composite? Stress in composite is P by A. So, that is equal to sigma C, right, sigma C. Now, if I keep on pulling it again, fibers fail and immediately all that load gets transferred to matrix and then matrix also fails. So, at that situation, what is the, so just a little prior to breakage, just at the point of breakage, P, which is the external load, will be load shared by fibers plus load shared by matrix, right. Now, what is the load shared by fiber? This will be equal to sigma F times AF plus load shared by matrix is what? Sigma M times AM. And this is equal to sigma C times A. Now, this is the general relation before anything is breaking. At break point, what is the value of sigma F? Sigma F will be sigma Fu. What is the value of sigma M? Sigma M will be the stress in the matrix at the strain level sigma Fu, epsilon Fu, right, breaking strain. And what is the value of composite stress? It will be sigma Cu, because the matrix, the fiber and the composite, all three are filling at the same point. So, I put all these things in above expression. So, I get sigma C U times A is equal to sigma Fu times AF plus sigma M evaluated at breaking strain of the fiber times AM. And if I divide this entire thing, so what is A? A is the cross sectional area of the composite. This is the cross sectional area of composite. AM is the cross sectional area of the fiber alone, AF of the matrix, and AF is cross sectional area of fiber. So, if I divide this entire thing by A, I get sigma Cu is equal to sigma Fu Vf plus sigma M at epsilon Fu, breaking strain of the fiber, times Vm. But Vm is what? If there is no air in the system, if there are no voids, then Vm is nothing but 1 minus Vf. So, this is when the situation. So, this is the strength of the composite for case B. This is the strength of the composite for case B. And when is this case happening? When fibers are in reasonable amount. When fibers are in reasonable amount. So, when fibers are in reasonable amount, this is my strength of the material. When fibers are extremely small, so that when they crack, the stress transferred to matrix is not large enough to cause it to break, then the strength of the composite is given by this relation. So, we will extend this discussion tomorrow as well, and we will conclude our discussion for today here itself. And tomorrow we will try to understand what is the meaning of very small, how small this volume fraction of fibers should be for the composite to fail in this state, and if the fibers are reasonably large in numbers, then when does it, at what level of volume fraction does this type of failure happen. So, that is what we will discuss tomorrow. Till then, have a great day. Bye.